Okay, welcome to the second part of the muscular system. This is mostly for the level 2 gym instructor qualification, but if so I'll be referring to sort of various page numbers as we go. But if this is subsequently used for another sort of form, the information is still probably largely the same. So I'll sort of try and talk through the presentation and relate it to the workbook that we're using for that. But I'm aware that sometimes the format of these books change, so apologies if that's the case. This is quite a long presentation, so I've got about 30 slides or so. So it might be best to kind of do it in two sections, or to kind of watch sort of 5 or 10 minutes and then go straight into your workbook and complete the workbook. That was how I've sort of done it in the order of the workbook. So hopefully it will make sense, and hopefully it'll give you a bit of guidance. So let's crack on. So last time I was looking at the kind of the structure of things like smooth muscle. So we looked at the different muscle type, and so we looked at the three types of muscle. So we had cardiac muscle. So in this picture we've got a heart, and the heart at rest is pumping about just under 6 litres a minute. But when we're exercising, it goes up to just under 26, or potentially goes up to around that amount, depending on your heart size, depending on your blood volume, depending on your levels of fitness. What's quite interesting about this picture, and I'm just going to sort of highlight a couple of bits. Look how much of blood flow when you're resting goes to the gastrointestinal tract, so the stomach and the intestines. Just under a quarter, so quite a chunk. But actually, when we exercise, only 1%. So yes, it's 1% of a much larger amount, but it's still a significant decrease in flow. So that was what I was trying to sort of hint at last time, in that actually when we're at rest, the blood vessels in our digestive system kind of open up, they dilate to allow blood in. But when we exercise, blood vessels constrict. I'll find the best way to do it. Constrict, like so, to limit blood flow to that digestive system. And you can see actually where it goes, because when we're resting, about a fifth of our blood goes to our skeletal muscles, and when we're exercising, 88% or so goes to our working muscles. So that was all done by smooth muscle. Well, number one, cardiac muscle beating much faster, but then smooth muscle dictating the flow of that blood, dictating or changing the diameter of blood vessels. So that was a little bit about what was important last time. So let me just clear that off. So today, really what I want to do is the first bit's probably the more important. Well, we could do it all actually. Explain the growth structure of skeletal muscle, including connective tissues. Describe the components of a muscle fibre. Explain how the proteins in muscle fibre allow contraction to occur. We'll sort of hint at that. It's covered in more detail later on in your book, and explain the different muscle fibre types. So the first bit we come to is actually on page 21 of your workbook, and the pre-reading for this is on page 23 of the gym manual. So I would probably recommend just having a quick review of that before you go any further. I'll assume you've done it, and so let's just dig into what a muscle is. So you're asked to describe the basic structure of skeletal muscle. So if we talk about basic structure, we can say, well, here is skeletal muscle. It is largely made of protein. It has some salts and water. I think that's I think that's if you sort of ground it up and really separated it into its component parts. Lots of structures are combined with water when you make this. Not like you wring out protein, you'd wring out a muscle and all this sort of water would fall out the bottom. But generally we can describe it as being made up of proteins, and a lot of those proteins are hydrated. The important pictures is this one. This is where you really start to describe the basic structure of skeletal muscle. Now, what we've got here on the picture, of the young chap bending his elbow, they've taken a sort of slice of muscle. So the first thing to explain with muscle is that muscles are joined to the skeleton by tendons. So you can see on the left hand side up here we've got our tendon. So there'll be a tendon at the other end. So tendons transmit force. Tendons are really tough. They're not particularly flexible because they're used to transmit that force of muscle. So when a muscle shortens, it pulls on the tendon, and that allows movement to be created. So continuous with that tendon all the way through that muscle is connective tissues. And the connective tissues play a couple of different roles. A lot of it is about force transmission. A little bit of it is that if you look at that picture, you can see even in the forearm there's lots of different muscles, and when the arms are moving, those muscles need to be able to glide past each other. So the first connective tissue we're going to consider is we have, where I'm just outlining here, we have a connective tissue surrounding a whole muscle. And this is, you might sometimes see if you're cutting up meat, for example, it looks almost like you can sometimes get a sort of, almost like a cling filmy sort of sheen over, but more visible on things like red meat. But you also sometimes see it under the fat layer in something like a chicken breast, like a really thin layer of almost like cling film. So the connective tissue surrounds it, and this is called the epimysium. So the epimysium covers that whole muscle. It allows it to glide past other muscles. It also means if there's any sort of infection inside that muscle, it doesn't immediately spread out to the surrounding areas. Inside that larger muscle, it's broken up into groups of muscle fibers called fascicles. So here is a fascicle that's labelled. So fascicles are bound by a connective tissue called a perimysium. A perimysium, it surrounds that group of muscle fibers. And that again helps kind of, so individual muscle fibers, when they pull, they kind of need something to pull along. So the perimysium provides a bit more strength to that muscle. It allows it to transmit force right the way through the body of that muscle. And it also means that as it's surrounded by connective tissue, it has a bit more kind of elasticity. If it's extended beyond its sort of end range, the connective tissue will help it sort of resist that stretch, but also sort of ping back into position. So the three layers of connective tissue are finished with this endomysium, and what we got at the end here is a muscle fiber. So do you see how that muscle fiber fits into a group of muscle fibers surrounded by a connective tissue that was called a fascicle? So muscle fibers themselves are made of little rods of protein surrounded by a really thin layer of connective tissue called an endomysium. So the epimysium covers the whole muscle, the perimysium surrounds groups of muscle fibers, and the endomysium surrounds individual muscle fibers. So that's the first thing you need to get down if you're describing the basic structure of a skeletal muscle. So it may be worth pausing and just getting clear your thoughts on that now before we go any further. So if you've struggled to kind of write down what we just went through, try and use this frame that I've described here. So I recommend you just pause here and just think about what you're going to add. So skeletal muscle is what gives our body the ability to, you could put anything like move. This doesn't get much better. By weight, it is made up of, and we saw the percentages earlier, water, proteins and salts. Covering the whole muscle is a layer of connective tissue known as the, began with an E, and groups of muscle fibers known as fascicles are covered by, you could say, a connective tissue known as, began with a P, whilst individual fibers are surrounded by, again, another thin layer of connective tissue, and you can explain what that's called, began with an E. So there's a nice structure to begin your explanation of the basic structure of skeletal muscle, and that should take up maybe the top third of your explanation. So here's a slightly more basic picture of what was being shown before. Already you can look at that. You can see that those little, you can see that sort of connective tissue on the outside. You can see those fascicles, those groups of muscle fibers, and at the bottom you can start to see an individual muscle fiber surrounded by a connective tissue, and you can see a little rod sort of poking out the end. So we're going to have a little look at those rods and see what they are. So we've got the tendon there. There we go. We've got the fascia, a connective tissue. So the epimysium is that connective tissue surrounding the whole of the muscle. You sometimes also get this much thicker connective tissue called a fascia on the outside. We don't need to worry too much about that. Just consider the epimysium as being our connective tissue covering of the muscle. We have the perimysium surrounding the fascicles, and we've got the endomysium surrounding individual fibers, and there we've got the muscle fiber. So where we're looking now is what's called a myofibril. So in a muscle fiber, muscle fibers are muscle cells essentially. So if you've ever looked at a cell under a microscope, it has a membrane, it has nuclei, or it has a single nucleus, or sometimes multiple nuclei, and they do specialist things. So muscle fibers are muscle cells, and to allow them to do their specialist things, they have rods of protein inside called myofibrils. So we'll look at those in a tick. And give you a nice sort of understanding of what they look like. So we've started with the connective tissue coverings. We're now going to look at the protein element of muscle. So this is a nice complicated looking picture, but I'm just going to try and sort of hone you into the right places. So this is again the basic structure of skeletal muscle, and we're going to look at the muscle fiber. So where we were on that previous picture, and it may be useful to sort of shuttle back occasionally just to outline it. So what we got to was a muscle fiber here. So remember, a muscle fiber is surrounded by a connective tissue. So what's quite interesting, if you can look at this picture on the bottom, if you turned it so the fiber sort of looked head on at you, what you'd see is the sort of the covering of that fiber. So if you can remember what that covering was called, your top of the class, that is of course I can't type on this thing. It's the endomysium. There we are. There must be an easier way. Endo. Can't do that any longer. Now, what you'll then see is rods of protein. So the muscle cell is surrounded by an endomysium, and then if you looked inside that muscle fiber, you'd see a rod of protein there, and rods of protein there, and rods of protein there, and rods there, and rods there, and rods there. So it would be full up. And so what you see on that bottom right hand picture is essentially that now side on. So on the left hand side, I've basically taken a fiber, chopped it and shown it to you, and you can see all the way inside there's these rods of protein. And now that picture on the bottom right is it just from a side on view. So muscle fibers, if we go up here, muscle fibers are surrounded by a cell membrane and the connective tissue endomysium. So that's what I described, or tried to write on their end. So the endomysium surrounds individual muscle fibers. Inside those individual muscle fibers, you have loads of rods of protein. So the proteins, are why we eat protein to build muscle. That's where it is. It's in that individual muscle fiber. So as we get stronger, we don't get more muscle fibers, but our muscle fibers get more protein in them. So the proteins are called myofilaments. So the protein rods are called myofilaments, and it's those things that help muscles contract. What you can see in that bottom picture on the right hand side, can you see how if you sort of kind of step back from it a little bit, there's a very dark band and there's a very light band. So if I just show that here, can you see where my arrow is going? That's darker than this bit. And what causes its darkness is the fact that we've got two different types of protein in those myofilaments. So we have a thin actin filament and we have a thick myosin filament. So we've started off with a connective tissue surrounding a whole muscle. We've broken it down into those fascicles, each one surrounded by their connective tissue. We've then gone to a muscle fibre. We've seen that it is made up or is surrounded by a really thin connective tissue, and then inside we've got all these rods of protein. And the rods of protein are made of two different types of protein, one thick myosin and one thin actin. So we'll just go over the page now and we'll start to have a look at what causes those to, or what they do in the body. Let me just erase this. There we go. Speedy. Okay, so that's the picture that I just showed, and you can see that there's a thick sort of dark stripe and a thin kind of lighter stripe. So what you've got to imagine is in a muscle fiber that's repeated, hundreds of times. So we've just taken a tiny segment. This is called this is kind of called a sarcomere. So let's just dig in a little bit deeper. So there's a sarcomere. So this is the sort of functional unit of a muscle fibre, and we've got to imagine that is repeated and repeated and repeated. So what we see now is a little bit more detail about how that thick filament and that thin filament differs. Can you remember the name of the thick filament? And can you remember the name of the thin filament? So the thick filament was myosin and the thin filament was actin. Now, let's have a look at a couple of bits. So, can you see, let's try and draw some stuff on. So, here's what's called a Z disc. Can you see that? So the Z disc kind of anchors each sarcomere. They're interesting actually. Z discs are one of the things that when you hurt the day after exercise, it's those things that are torn. It's not lactic acid. Lactic acid clears pretty quickly from the body. But when you really, that sort of pain you get a day, 2 days after, it's these things tearing. It's them creating inflammation. So those Z discs anchor the proteins. So can you see the thin filament of actin? So if you just look, the actin is in yellow, and I just want you to just kind of really stare into the screen and look at actin. And so you can imagine we've got an actin filament on one side anchored by a Z disc, and we've got an actin filament on the other side anchored by another Z disc. So they're pretty stable. So the actin on this side also, well, I'll draw it in actually. Can you see where I've got, well, we've got one actin filament going in that direction, and I've got one actin filament going in that direction. So each Z disc has actin filaments going that way and actin filaments going that way. So they're sort of supporting that whole structure. Now, I want you now to look at the myosin filament. So look at that thick myosin filament, and what you should see on it, can you see those almost little like golf club heads on it? And what they do, so the little golf club heads, the ones on the right hand side, they are able to clip onto that myosin and they move it. So the two heads, so the ones on the right hand side clip onto the actin filaments and they wiggle it that way, and the other filaments on the other side take that other side and wiggle it together. So what you get is you get myosin filaments on either side, or myosin heads on either side of that myosin filament, and they move the actin inwards. So what you see is as the myosin moves, the filaments are drawn together. So they close that gap. So the myosin heads on one side go that way, the myosin heads on the other go that way. The myosin doesn't change, the myosin length doesn't change, but it pulls the actin closer together. So it pulls it, so you close that gap between those two actin filaments. So that's the basis of something called the sliding filament theory, and that's what we'll look at later on. But for the minute, we just need to kind of just go over the fact that within that muscle fibre, we've seen the fibre surrounded by the endomysium. We've seen each muscle fibre made up of protein rods called myofilaments, and we've seen that those myofilaments are made of two types of protein, one thick myosin filament and one thin actin filament. And that's your basic structure. So here's that sarcomere. nice and close, just to kind of reiterate, just a bit sort of bigger for you. So we just need to see the myosin heads, or the myosin have heads that can attach to actin, so they clip on, and then they swivel. They detach, they clip on, and then they swivel. They detach, they clip on, and then they swivel. So what powers that swivel? Well, that's the energy that you use. So this is why we eat food for fuel. It's powered by our body's energy currency. So myosin heads do the contraction. Actin have binding sites to allow myosin to attach. So as long as that binding site is exposed, myosin can clip on, swivel, and help draw that space together. And here's a nice sort of big, complex looking picture. I'll go through it a little bit now, but don't panic if it doesn't sort of hit home. I'll label something on the diagram, and that's as much as we need. Well, let's label two things. So do you remember the Z discs? Here are my Z discs. My Z discs are also down here. So there's a Z disc. Remember, those anchor those actin filaments. Now, what I want you to see is this area here. This is called the H zone. I'm going to give up trying to write zone. H is enough. There we are. So can you see down here in this picture below the H zone there? So the H zone represents the area where all you see is myosin. So do you see how if you go to the either side, myosin and actin overlap? So in that picture on the top, you've got quite a wide H zone. So when a muscle receives a nerve impulse, it initiates a chain of events that allow the binding sites on actin to be exposed. That means the myosin clips on. So what does it do then? What does myosin do? Well, it should swivel and then detach and then reattach and then swivel again. Then detach and reattach and swivel. So what's that going to do to the size of that H zone? You should see down the bottom that as the myosin draws actin together, it decreases the size of that H zone. So do you see on this picture how wide the H zone is, but down here it's much smaller. So in terms of understanding the muscle fibre, hopefully you can see the distinction between thick myosin filaments having their myosin heads and thin actin filaments having their binding sites. If you were asked to describe a sarcomere, you could mention the Z disc anchoring that actin. You can show where the myosin filament goes, and you can see that H zone, when you're relaxed or when the muscle's relaxed, is much wider than when it's contracted. Oh, here's a quiz. I think there's one question I should have put much later, but here's a quick quiz. I just want you to pause the presentation, and while you do that, I just want you to put these in order of size, largest to smallest. Endomesium, epimesium, and perimesium. Then the muscle fibers we haven't really done yet, but maybe you could have a quick go at it. Type 2A, type 1, and type 2B. That may mean nothing to you yet, so don't panic. And lastly, the myofilament, a fascicle, a muscle, and a muscle fiber. So pause the presentation whilst you figure that out. And so here's the answers. So remember, we have an epimesium surrounds the whole muscle, the perimesium surrounds the fascicles, and then we have an endomesium surrounding individual muscle fibers. The biggest muscle fibers, we'll go on to this in a minute, is type 2B fibers. These are big muscle fibers. They contain lots of protein. Type 2A fibers are not quite so big, and type 1 are quite small. And we'll look at what other differences they have between them. If we go through the smallest to largest, I think I've missed a couple off actually. We should have started with a muscle. The muscle. The muscle is broken up into fascicles. Fascicles are made up of fibers, and then if you look in a muscle fiber, you'll see myofilaments. They're protein rods, and if you looked at one of those and took the tiniest unit of it, you'd call that a sarcomere. So where you're asked to describe the basic structure of skeletal muscle, this is quite a nice frame to consider that from. So it may be worth just pausing after I've just run through it with you, and then completing your workbook to describe that basic structure of skeletal muscle. So just begin by saying what skeletal muscle is made up of. Proteins, water, salts, and if you can get the concentrations, that would be great. State what the connective tissue that surrounds it and what perimesium is. That should say what. Explain what the endomesium surrounds. Explain that a fiber is made up of filaments or myofilaments, and then just list those two proteins, the actin and the myosin. Explain that the myosin has got these swiveling heads that allow the power to contract, and explain that thin filaments have got binding sites for those myosin heads. Explain that to contract, myosin heads swivel to draw those thin filaments together. If you like, you can mention that in a sarcomere they shorten that H zone. So a lot of this work is on page 23 of your manual. So take a pause, and if you're ready, go and complete your workbook. So this section asks you to just briefly consider the pelvic floor muscles. To be honest, in your everyday role as an instructor, you may not give a huge consideration to this, but particularly if you work with antenatal and postnatal clients, this may be a consideration. And if you're thinking of doing something further like Pilates, the pelvic floor is an important muscle. You can pre-read by looking at page 28 of your manual. In a minute, I'll give you the opportunity to fill in page 24 of your workbook. So here we've got a nice picture from above of your pelvic floor muscles. So the pelvic floor muscles, if you can see, this is kind of forming almost like a basin inside the pelvis. So I do have a pelvis actually somewhere. Good. Where's it gone? Who's nicked it? There we are. So this is the pelvis. So what you can see is that, and so this picture is effectively from that angle. So what you see is, I struggle with this camera. What you see is these pelvic floor muscles are kind of right underneath here. So they form a basin under that pelvis, and they support, particularly in women, your reproductive organs, and women, their uterus, but they also support the intestines, and the bottom of that digestive tract. So if these are dysfunctional, if these have got sort of collapsed or damaged, then it can have quite a large effect on things like continence. So you don't accidentally wee or relieve yourself, but also can affect things like sort of digestion as well. So the pelvic floor form a muscular sling under that pelvis, so it supports the contents above it, and they run from the pubis at the front to the coccyx at the back. So if I just show on here where those are, so you can see this is the front of your pelvis, an area called the pubis. So again, if you look on here, where's it gone? So there's your pubis there. So that's the part called your pubic symphysis, and there's your pubis there. At the back, just can't get this right today. There we are. So there's your sacrum, and this is your coccyx at the bottom. So the muscles connect the pubis at the front to the coccyx at the back. So you can see that also piercing through those muscles, there's the area where you will defecate through. So you can sort of see the importance of these muscles in maintaining elements of continence. So they support the pelvic organs, the bladder, which sits on top, and the intestines. So they maintain continence and also help in the birthing process. So they actually stop the baby actually sort of slipping too far down. So this is from the bottom up. So this is kind of looking at the pelvic floor from underneath. So the key muscles are the levator ani group. So that's these ones here. We don't need to know the individual names, but it's quite useful to just see broadly where they are. These are called pubococcygeus and iliococcygeus. So you can see here on this picture. So this area at the back is the coccyx and the sacrum, and you can see how those muscles sort of blend out from there. You can see here how they'd support the anal sphincter, and then here we've got, that's annoying, that stop. You can also see just above that you've got the opening for the urethra. So the pelvic floor muscles are the levator ani group, those two there, and you can also see there in bold on that right hand side a muscle called coccygeus, so attaches onto the coccyx. So that's just quite a nice summary. If you want to read up on it, as I suggest you do, it's on page 28. Now might be a good time to fill in your workbook, just using those key terms, just explaining that it forms that sling underneath the pelvis. It supports continence and the birthing process, and just show you a broad understanding of that region. So now's a good time to pause. So we're up to page 24 in your workbook. We've just covered the pelvic floor muscles. We've done about 40 minutes now, so it could be a good time to pause, maybe pick it up in a few minutes, or maybe on another day. So I'll keep going and go through the last section. There's just another sort of 12 or so slides that cover some really important stuff. So let's press on. So we're going to cover briefly the roles of muscles. So these are terms you may have covered before. The concept of a muscle being a prime mover. So when we look at muscle actions, we may talk about a muscle being a prime mover. So if I was doing a bicep curl, my bicep is the prime mover. So to allow that to happen, this muscle has to shorten. So the bicep shortens, and the tricep underneath has to lengthen. So the agonist, or the prime mover, is the muscle which is contracting to produce movement. The antagonist, in this case the tricep, needed to relax to allow that prime mover to do its job. So you can imagine if I was kicking a ball, my quadriceps are going to be the prime mover, and which one is going to be the agonist? Also the antagonist. It's going to be the hamstrings. So wherever movement is taking place, there'll be a group or muscle group that is contracting, shortening, and there'll be another set of muscles that are relaxing to allow that movement to happen. We might sometimes see muscles that act synergistically, so they modify the movement of an agonist. So in something like a bicep curl, for example, I've got muscles of the forearm which also contract to allow that movement to take place. So they kind of help out. We may also have muscles that are called fixators. So again, if I want to create a big powerful movement from my biceps, I have a head of bicep attaching onto the scapula. If that scapula is not stabilized, I won't be able to pull through that muscle with much force. So the fixators fix the scapula to allow the bicep to pull. It's the same way, even in running. Sometimes the abdominal muscles need to fixate the core to allow you to really express power from your limbs. So fixators stabilize body parts to allow muscles to then perform their action. So we're just going to go on to a few contraction types. So this is the difference between concentric and eccentric contractions. So what we see here is on the right hand side we've got a nice picture. It's a bit sort of detailed, but I think it's quite a nice one. Do you see what I was saying earlier about how the bicep, so let's do that. You see that belly of the bicep brachii. If you really trace that up, you can see how that head attaches into that scapula. So I think that's quite a nice thing to note first up. Now, what you see, the difference between the left and the right hand picture is the bicep. Do you see how much shorter it is? So it's almost kind of short and fat. So that shortening has allowed to pull on that radius, that forearm muscle, and it's created elbow flexion. So it's pulling up like so. So it's there. Now remember what has to happen the other side. The tricep needs to relax to allow that to happen. So the agonist is contracting, the antagonist is relaxing. Now, that classic movement of the bicep is what's called a concentric contraction. So remember, that's contracted, the triceps have relaxed. Now, once we're at the top, let's say I've got a really heavy weight. How do I get that down? Does the tricep need to contract? No, it doesn't. To lower, the bicep still contracts, but it does it whilst lengthening. So we call that motion an eccentric contraction. So wherever a muscle contracts whilst it's lengthening, that's called an eccentric contraction. So if you think about something like a bench press, that lowering phase, you're working the same muscle groups that you're going to use on the way up, but just a different type of contraction. It's eccentric contractions that really cause that kind of ripping of muscles. They tear the Z discs, which gives you that pain the next day. So heavy eccentric contraction is that lowering phase usually. So an example here on the concentric contraction is that upward phase in a bicep curl. So the muscle shortens, muscle moves. So bicep shortens, elbow flexion takes place. If we're squatting from that lowered position, as I go up, the quadriceps are shortening, the gluteals are shortening, and they're creating a concentric contraction to drive you upwards. As you lower, those same muscle groups are working, but they're just lengthening as that muscle contracts. So it's almost sort of feels a little unnatural sometimes, you know, that control, because the muscle's lengthening, but it's also got to coordinate the fact that it's also contracting. So an eccentric contraction, lengthening whilst contracting, concentric, shortening whilst contracting. So this is just a nice picture of someone doing an isometric contraction. So iso in, I think it's Greek or Latin, means same. So this is same length. So the muscle's contracting, but it remains the same length. So remember earlier I was talking about muscles acting as fixators. So they fix body parts to allow muscles to maybe express power. So we can imagine that, for example, when my trapezius and the other muscles around my shoulder girdle contract around that scapula to stabilize it when I do my big mighty bicep curl, they're contracting isometrically. So they're fixating that muscle joint, or that joint. So the muscle contracts and no movement is created. You use it to hold postures. So, you know, just generally as we're stood, muscles will tend to work isometrically, but there's a number of sports where you even just think about golf or something where you're at the address, you know, your muscles need to work isometrically to just hold that nice posture before you play your shot. There's lots of situations where you can use isometric contractions. So it's used to fix joints like the scapula to prevent unwanted movement and to allow agonists to contract with force, or just as this chap's doing here, just to hold poses, which is a part of all sporting movements. So the value of it really is, you know, this guy, to do that, he will need to train isometrically. You know, lots of his work will be about big, powerful movements, but to train to do that, he needs to train his muscles, his nervous system to do that. And we have this term that sometimes you hear. I literally never use this term, so I'm going to spend about 30 seconds on it. You sometimes see this term isokinetic, and that means a muscle is moving at the same speed. So you can see this chap here has got a specialist piece of equipment. This is really the only way you can kind of guarantee that regardless of the power of contraction, you're moving it at the same speed. So you see it a lot in, or used to see it a lot in lots of rehab settings. I don't know if you see it so much now. You might prescribe exercise to work at the same speed, but it's not a term that I come across a lot in my world. So if you see it, that's all it means. ISO, remember, same, and then kinetic means speed. So we're now going to look at just describing joint actions and specific muscle group actions. Again, this is in your manual, and this is on page 27, so it could be just quickly useful to quickly review the terms in that before we go any further. But I think it should be something that we can accumulate as we go. We've got someone here doing a nice body weight squat, and what you can see is their knees and their hips are the primary sort of joints that are moving here. So we need to be able to describe what movement is happening. So as she moves from that down position on the right hand side, what has to happen to that knee and that hip to get her up? So just have a think about how you describe that. And this should be quite a straightforward-ish one. So what we see at the quadriceps is we see knee extension. So in the picture on the right hand side, on that lowered position, we've got knee flexion. So to get upwards, the knees, the quadriceps contract to create knee extension. The hips combine using the glutes or the gluteus maximus to create hip extension. So in that picture on the right hand side, her hip is flexed, so the angle between the so the angle here is in flexion. So do you see how we're decreasing the angle here? That's flexing, and so when she's standing up, that's hip extension happening because of that gluteus maximus. Here we've got a bench press. So what's happening at the shoulder and the elbow? Have a look through the table on page 27, or I think it may be 28 in your manual, and just see if you can describe the joint actions that are happening at the shoulder and the elbow. So at the chest, we've got a movement called horizontal adduction. So adducting is drawing the limb towards the midline. So if I was standing and my arm was out, bringing it down towards my midline is adducting, adducting. Bringing it out is abducting, taking it away from my body, abducting. So when it draws towards that midline, we call it adduction. Now, because I'm across here, we call that horizontal adduction. So the pectorals produce horizontal adduction, whereas at the elbows, the triceps create extension. And if you want to know what's happening on the lowering phase, you just reverse it. So horizontal abduction, abduction, and elbow flexion. Remember, that's all being lowered, the same muscles, just working eccentrically. So here we've got a chin up, or pull up. What's it? Chin up, this one. Yeah, I always get them confused. So again, just think about what's happening at the shoulder joint and the elbow joint. So just look in to elbow, and you can see we have a narrower angle flexion. You can also see, if you just follow that elbow, you can see that to get there, this elbow has been drawn in to that midline. So what do we call that? When a joint is drawn to the midline, we call it adduction, adduction, adduction. So you can imagine the opposite, something like a shoulder press, exactly the opposite. So it's going to be elbow extension and then shoulder abduction. So shoulder abduction happening here. You can see the person there doing some lateral raises. So quite a nice, simple movement happening at the shoulder, drawing that arm away from that midline, AB abducting. So On page 25, 5.8, there's a section that says identify the joint actions brought about by specific muscle group contractions. So you can use your workbook, you can review whatever's in there we've just been through, and I want you to describe the joint actions brought about by these muscle groups. So what's going to happen at the quadriceps? So this is knee extension. What's going to happen when the hamstrings contract? They're slightly combined with that one, so you might need to hit your books. Gluteals, or gluteus maximus. Biceps. Triceps. The lats. And the deltoids. So in that space, you need to write in what joint actions are going to occur by contraction of those muscles or muscle groups. So pause the presentation and complete that, and we'll go on to the last section, which is about muscle fiber types. Okay, so I sort of threw in a question earlier that was maybe a little bit premature, but it was really related to the different muscle fiber types. So muscle fiber types is quite an interesting concept, because we're kind of largely born with a lot of our sort of physical characteristics. We can train, but it helps. For example, if you wanted to be an aerobic performer, it helps if you've got a lot of one particular type of muscle fiber, known as type 1 fibers. Whilst if you're going to be a sprinter, it helps if you've got much more type 2 fibers. So a lot of characteristics are kind of inbuilt, really. So I want to sort of just discuss that a little bit now. So the concept here, you're going to be asked to identify different skeletal muscle fiber types and their characteristics. We can do it fairly quickly. So to begin with, we broadly categorize them into two groups. We have slow twitch fibers and we have fast twitch fibers, also known as type 1 or type 2. So you can have a single muscle, so let's say something like the muscle in your calf called the gastrocnemius. So that is a quite powerful muscle. You see it in some athletic people when they've got this big sort of bulbous muscle at the back of their calf. Now, this is quite an important muscle for sort of springing off. So a lot of people have got quite a high concentration of type 2 muscle fibers in their gastrocnemius. It's a fact. But you don't just have type 2 muscle fibers in that muscle. So someone may have, let's say, 50% of type 1, 50% of type 2. Someone might have 60% of one type and 40% of another type. So the amount of type 1 or type 2 fibers really depends on a little bit of genetics. If you look at the muscle underneath that, we've got a muscle called soleus. It plays a bit more of a postural role in our body. So in your calf, if you just stand up, you just sort of, to just keep you upright, to keep you stable, that soleus just contracts, sometimes isometrically, to just keep you nice and upright. It's a postural muscle, a bit like we have sort of postural muscles running all the way up our deep spine, in our abdominal muscles, deep in our neck. But these postural muscles need to do that contracting for long periods of time. So they have to be quite efficient with their energy, and they need to be a little bit more aerobic. So you might find in postural muscles, you get more slow twitch fibers than you get fast twitch fibers. So this is kind of another reason why we have these two different types. So here's a nice picture that just shows a few differences in muscle fiber types. So we're still looking at broadly slow twitch versus fast twitch. Now, slow twitch fibers here are generally much darker. They'll have a higher concentration of a substance called myoglobin, and that sort of sucks oxygen out of blood. So it transports oxygen from the blood and delivers it deep into that muscle fiber. So it means it has a very efficient system of transporting oxygen into that fiber. You see it in chickens, actually. If you have a chicken thigh, it's generally a darker meat. Chickens spend all day sort of stood up usually, and so as a consequence, that meat's slightly darker than the breast, which is a sort of whiter protein. So the fast twitch fibers are much paler. They have less myoglobin. They're not so good at extracting oxygen from the blood. Do you see also, if you look at the diameter of a fast twitch fiber, do you see how they're much wider? So they're thicker, they're stronger. Because of that improved oxygen concentration, or that improved oxygenation of slow twitch fibers, they're much more resistant to fatigue. So this is why you find them in postural muscles, sort of deep, and why if I was going to be a runner, I'd want, or a long distance runner, sorry, I want a large amount of slow twitch fibers. And this is why maybe Usain Bolt is never going to make a marathon runner, and why maybe Mo Farah was never going to be a 100-meter sprinter, because we're born with different concentrations of type 1 and type 2 fiber. So Usain Bolt will be very pure type 2 fibers. You know, he just needs that explosiveness. He'll have a really high concentration. So if you're presented with a table where you're asked to identify skeletal fiber types and their different characteristics, you can start with something like this. So in page 25, you're asked to do this. You can kind of summarize this same information on your sheet. So slow twitch fibers on the left hand side, they're rich. They're red. They have a rich blood supply. The myoglobin gives it that redness. They'll also have maybe more capillaries going into them, but it's mostly that myoglobin which gives it that colour. They're really suited to aerobic activity because they're so fatigue resistant. They have a high number of what are called mitochondria. So mitochondria are your cells' powerhouses. They create energy. They're relatively weak, or they have a relatively low amount of force, and also the speed of contraction is slightly slower than a fast twitch fiber. It's in the name. So they're slow to fatigue, but also relatively slow to twitch. When you do any sort of activity, your body wants to use the slow twitch fibers first. So if I do something like a bench press and I use a really low weight, I can just go for ages without really activating any fast twitch fibers. If I want to activate those fast twitch fibers, I have to raise the intensity of that exercise. I need to put a large amount of weight on, so I really have to force it. I really have to drive my body to cause those type 2 fibers to contract. So the type 2 fibers, at one end of the scale we have these fibers called type 2B. These are really pure fast twitch fibers. They're white because they have a relatively poor blood supply and relatively little myoglobin to shuttle that oxygen from the blood. They're really suited to anaerobic activity, burst type exercise, sprinting, powerful movements. They have a relatively low number of these things called mitochondria, your body's or your cells' powerhouses that create energy. They produce a large amount of force. We saw they're much bigger. They're really thick fibers, so they'll have more protein filaments in them, and protein filaments that contract quickly. But they are quick to fatigue. Now, in between it, we're born with these things called type 2A fibers. These are like type 2 fibers, but if you train very aerobically, they take on more aerobic qualities. So they get more mitochondria, they improve their ability to resist fatigue. If we train very anaerobically, they take on very anaerobic properties. They become powerful, they become bigger. So essentially we are born with fiber type almost kind of given, but we have the capacity to train towards a particular fiber type. So this is quite why maybe if you're, let's say, it shows you the difference between training for endurance and training for something like strength. So if I was training for endurance, I'll only ever really hit my type 1 fibers, maybe some type 2A fibers, but unless I'm really using decent sized weights and training at real high intensity, I tend not to hit those type 2B fibers so much. In the same way that if all I ever do is powerlifting, I may just get those type 2B fibers, but not much of the type 1 fibers. So quite often people like bodybuilders, you see them train with a moderate to heavy amount of weight, but actually for quite a long time, their sets are relatively long sometimes. And that's in an attempt to try and hit type 1, type 2A and type 2B fibers. And certain techniques you'll learn later on, or certainly if you went to level 3, you use different reps and sets ranges to hit different parts of those muscle fibers. So you might use a kind of a wave loading pattern where you do large sets with not so much weight, and then a few sets with loads of weight. So you kind of hit all those fibers along the way. So you're asked to describe, or you're asked to identify skeletal muscle fiber types and their characteristics. So again, I've got a nice little frame that you can use. So just begin. So again, you might want to pause this after I've explained. You just want to explain the muscle fibers within the same muscle can vary depending on the fiber type. So you could, as I said earlier, you could have, say, a quadricep or a gastrocnemius muscle, and that has a number of different fiber types. You could explain that you can classify depending on the speed of contraction or twitch broadly into those type 1 and those type 2 fibers. You then want to dig a little bit deeper, so explain that the colour of type 1 fibers, explain their size, the diameter, the speed of their contraction, and what activities they're suited to. You might also include the number of mitochondria and how resistant to fatigue they are. And then do exactly the same for type 2 fibers. So explain that they're white, they have thicker diameter, or they're the wider diameter, they twitch more quickly, they're far more powerful, but they have fewer mitochondria, they have a less myoglobin, they have a worsened aerobic ability, they fatigue more quickly. You can then explain how type 2 can be subdivided into those type 2B at one extreme and then type 2A fibers in the middle. So you can explain that if you train aerobically, they take on more type 1 properties, and if you train anaerobically, i.e. lots of strength training, powerful movements, they become much more like pure type 2 fibers. So I would suggest pausing the presentation, complete your workbook, and then we're nearly done. So the end product was, hopefully you can identify and define characteristics of and functions of the 3 types of muscle tissue. That was done in the previous presentation. So we're looking at the difference between cardiac, skeletal and smooth muscle. We looked at the basic structure of skeletal muscle. So we looked at the broad connective tissue coverings, the epimysium on the outside, the perimysium surrounding fascicles, and the endomysium surrounding muscle fibers. We dug a little bit deeper and looked into what was a myofilament, and we looked at the fact that those little protein filaments had special or quite clever properties. So we had thick myosin filaments that had those little golf club shaped heads on the end that could swivel. We had the thin actin filament that could allow the binding of those myosin filaments to draw together those actin filaments to compress that H zone and create contraction. And then lastly, we looked at the different fiber types and their characteristics. So we saw that we had type 1 fibers, which were very aerobic, very dark red because of this myoglobin, this great oxygenation, loads of mitochondria. On the other end, we had very pure type 2b fibers, white, very poor blood supply, likely to fatigue, but big, powerful movers. So hopefully you've had a little dig into that and managed to complete a lot of your workbook along the way. That brings to a close the basic anatomy of the musculoskeletal system. The next thing to look at is really how different populations, muscles and skeletal systems differ, and the sort of considerations we need to make as instructors. We also need to consider the energy systems and what provides us with our energy as we exercise, and how we can create programs to make them adapt and change in the way that we want. So thanks a lot. I hope you found it useful.